Hello all. So in this video, we'll be discussing an paper from Google. So you can see it is published by Google, and the paper is titled as "Attention is all you need." So basically, they described here the language translation that is used. So what is the architecture that is used in language translation? So previously, let me start with some traditional models before this uh, paper. So uh, it was like encoder decoder based model. So we know that what is encoder decoder based model. So it is, there is one encoder and there is one decoder, and inside the encoder, like we can use anything like CNN. Maybe for language translation CNS, there is one paper based on CNN as well, but RNN, LSTM, even by LSTM can be used, and there are papers for that. And as we all know that whatever is the output of the encoder will go as input to the decoder, and based on that we'll get the output. So for instance, let's say we have one word that my name is Parth in English, and we have to translate it in German. So what we'll get as the output is meine Name ist Parth, right? But this was a simple sentence, and it is also a very small sentence, like not like very much big sentence. So we can see that it's easy based on this models. But what if the sentences are bigger? So this is what they try to explain through this paper, that why attention is most useful thing in language translation, especially, which is why I'm particularly targeting language translation, because this paper I'm discussing and they revolves around language translation. That's why. So let's try to see that what they have done perfectly in here. So what they did is that this is the architecture. So I'll try to unwrap all the blocks. So right now it's a total black box for you, but this is the input, and here we'll get the output. And what are all those things? We'll try to unwrap it. And after explaining, I'll come back through this model and I'll tick mark the blocks that I am completing the discussion, and then we'll move forward like this, and I'll show you the entire paper. All the 11 pages we'll go through, and for that we'll be using a super beautiful blog written by Jay Elmar. So he is the guy who like modified the, like not modified, but he modified the language and made it easy to understand for everyone. And he is also world famous in this NLP, and even he's having his YouTube channel, you can follow it. And this is the guy, okay, and he did this thing. So this is the transformer based model. Now this transformer based model is using attention, and after this lecture I'll be discussing the BERT, GPT-2, GPT-3, all this thing, and that will be very easy for you. Even you will read the research paper for BERT GPT at your own after finishing this research paper. So this is very important thing. Now let me start with very high level thing, that the entire block diagram that I showed you, it's just this thing, that input, this is some language, I guess French, and it is like, let's say ye suis udiant, so I am a student, that's the output. Now this transformer, as I said, we have encoder decoder, but previously we were having something else inside the encoder, but now we'll have something else, and that's why they are called transformer based model. So let me just try to go through all the steps. So here in this paper, we are just not using single encoder, but we are having 6 encoders stacked on top of each other. So that is that here, what is the output of the first will go to the input as second, and so on and so forth. So this is how it is there, and this is the final output of the entire encoder block, right? So let's consider this as entire encoder block. So this can be the final output of the entire encoder, and this will go to the input to the decoder. So we'll see everything in thorough detail one by one. So we can say that this is the decoder. Now let me just erase these things and move forward. That now inside the encoder, now we are focusing on just the encoder part. So what is there inside just this one block, and this are copied 6 times. So I'll just discuss one encoder block, and then it will be copied 6 times. Inside encoder, you can see there is one thing called self-attention, and there is a feed-forward neural network. So one is very simple, that is neural network, feed-forward neural network, that we all know. But let's focus on self-attention. So now what is self-attention? And the same thing focus follows here in the decoder part. But right now, let's keep aside the decoder part. Just focus on the encoder. We'll see decoder later. Now, firstly, what we'll do is very simple thing that we are giving input yes, Swiss, Udianta, and then we are converting it into the embeddings. So these are the embeddings. Let me just change the color to some dark. Yeah, so these are the embeddings, and this dimension is 512. So each and every word of the sentence, which are called tokens in NLP language. So this is one token, this is other, and this is another. All are converted into 512 as per this paper. You can use like any length. This is the hyperparameter, and you can tune it like as per your wish, and you might get better results as well. Now this will go at the input to the self attention, and then we'll get individual output z1, z2, z3. So now our first target is what are this z1, z2, and z3, and how we will get it based on this self attention. So let's just zoom into this thing. So what we'll do is now we are starting the actual encoding. So we are just taking, for example, two sentences, thinking and machines. This is just a lame example that we are just having two, sorry, words, not sentence. The one sentence consists of two words, thinking and machines. So this is the thing that I'll show you later. But what I can say is that why the self attention is needed. So you might ask the question that why self attention. So it's a very simple sentence here that the animal didn't cross the street because it was too tired. Now as a human, if I'll ask what is it here, so we can say clearly that it is referring to animal here. But what about the machine, that is computer? So it corresponds to animal. How computer can know it? Because while translating it, it should know in some other sentence that this it corresponds to this machine, right? And that is where attention is needed. So we can say that here it is written. You can see. Let me just try to erase it first, and I'll show you that here it is written that when processing the model, the word it self attention allow it to associate it with animal. So after this self attention, we'll get the output that the it is associated with animal, that the machine will learn it, right? Now if you are familiar with RNN, then think of how maintaining a hidden states. So as we all know that what is RNN, it's having the hidden states, and what it was doing was it was having the gradients, it is just like a state diagram, state machine, that one state then another state, so all states, it's a memory kind of thing. But it was having a problem of gradient descent. So the long term dependencies between two sentences, if the sentence is too long, so between two words, sorry, if the sentence is too long, then the relation between two words in that sentence, which is very much important, but it was not important because of we are using RNN, and that was a drawback of RNN. But as a human, we know that that two dependencies is important, and that's why RNN is not used nowadays. And also LSTM came, but LSTM also has some drawback, and we all know this thing. So I'm not going deep dive into that. So after that, you can see that this animal is referring to it, right? After the self attention, you can see this. And I'll suggest to go through the each and every line of this blog as well as the paper. And after watching this lecture, it will be just a couple of minutes for you to just go through entire blog and the paper. Now, let's try to have the very important part of the lecture, that is self attention. So the very first step is what we'll do is based on a word, we'll convert it into 512 dimension. So as per the paper here, 512 dimension, it's written that it's not necessary that you have to have 512, and it's like anything that you can use, as I already said, but they are using 512 over here. Now what we are doing is that we are multiplying all the input vectors. You can see here that we are multiplying this x1 with some matrix. And now you might ask, what is this matrix? So let me explain it, that what are this matrix. These are matrix is nothing but a neural network, because these are the weights w, and wq means query. So what we are doing is we are having one neural network, right? And we all know that in a neural network we'll be having one weight W, and this is one neural network and it is having weight W, and initially we know that the weight are initialized randomly. So we'll have random weight, and whatever is the output that we are getting from this neural network, we'll compare it with the actual output and we'll have loss, then we'll have back propagation, and then based on that we'll optimize our weights. So initially it will be random, but after the loss, like model will learn, this neural network will learn and it will adjust this weights W, and then we'll get our like loss as our loss will be minimized at the end and we'll get the better values of W matrix. So firstly what we are doing is we are multiplying x1 with this W and we are getting something like this, and you can see that here the dimension are small, so it's not like, so you can see the dimensionality is 64. So this new vectors that we are getting, so there here we are getting three things actually. Let me just erase this thing, that what we are doing is we are multiplying x1 to three matrices. So here we are having three different neural networks here. So previously in any model we don't have more than one neural network, but here itself in one model, and that's what is called the transformer model, that inside we are having three neural networks, you can see, and later we will see there is one more as well, and even at the encoder side we'll be having, right? So there are many neural networks in the same model. So here this is the first neural network, this one is the second, I'm not fully connecting it but it's connected, and this one is the third, and all are having different, let me write that this is WQ, then this is WK, and this is WV. So firstly what we are doing in simple thing, that embedding we are multiplying with these three matrices and we are getting some vector, and you can see these vectors are smaller, and here on this paper it is 64, right? So notice that the new vectors are smaller in dimension than the embedding vector, and their dimensionality is 64, while the embedding and the encoder input output vector have dimensionality 512, as I already said, and they don't have to be smaller, but this is an architecture choice to make the computation of multi-headed attention mostly constant. So this is what they are doing deliberately, because they need to do this, that the computation of multi-headed attention should be constant, and we'll see what is multi-headed attention. Firstly let's try to have self-attention, then multi-headed is just a simple thing. Now let's go forward, that what are these query keys and values, that will be clear in a minute. So these are just the abstraction that are useful for calculating and thinking about the attention. So it will be clear intuitively that why we are using this query keys and values. So let me just proceed. So first step is done. The first step was just to have the q1 q2 k1 k2 and v1 v2. So this was the first step. Here it's written in the bold that we have to calculate this q1 q k and v, that's it. Now after getting q1 k1 v1 and this like this, what we are doing is we are calculating one score. And what is this score? It's nothing but just the dot product of q1 and k1, and we are getting here as 112, because we know that dot product will be a scalar quantity between two vectors, so that's why we are getting some. And similarly what we are doing is we are calculating for q1 k1, then q1 k2, sorry, up till here we change some with the dark color, so q1 k1 and q1 k2, and we are getting these two things. After this what we are doing is we are having just dividing this by 8, and why by 8, because they have even mentioned here that why they are just using 8 here, that the third and fourth steps are to divide the scores by 8, that is whatever score we get we divide by 8. And why 8? Because it's the square root of the dimension of the key vectors used in the paper, and they used as 64, right? So that's why we are getting 64, and there's one reason as well, that this leads to more stable gradients. So they experimented and they got more stable gradients here, and that's why they used 64, and that's the logic behind using 64. Now what are we doing next is that we are applying softmax. So softmax will be nothing but we know that it will be e raised to 14 upon e raised to 14 plus e raised to 12, and similarly here e raised to 12 upon e raised to 14 plus e raised to 12, and we know that what softmax will do, it will give the probability distribution. So here you can see that we are getting this as the high probability value as compared to this. So we can say that we need to focus more on the word thinking as compared to the word machines. So the softmax code determines how much each word will be expressed as this position. So clearly the word at this position will have the highest softmax scores, but sometimes it is useful to attend to another word that is relevant to current word. So we'll see what does this mean in detail. So firstly, let's go to next step. So what we are doing after that is the fifth step is to multiply each. Now until now we haven't used values, right? The value vector that we calculated, it's unused, but now it's the time. So after what we are doing, whatever softmax score that we are getting, we are multiplying it with values. So whatever value vector was there, we are multiplying the softmax score. So intuitively, if you can think for a minute by pausing it here, that what we are doing here is that whatever probability, that is the thinking what is saying higher probability, so we are multiplying v1. And what is v1? V1 is some vector that we are getting by multiplying with some random metrics or some weights of the neural network. And whatever values that we are whatever value we are getting after multiplication of the softmax and the value vector, let's say it is called v1. So this is v1 and this is v2 modified, right? Just it will be multiplied, all the entries of the vectors will be multiplied by 0.88 and here 0.12. We can see that this will be very like, because it is multiplied by value which is near to 0, so v2 will not be more, right? But v1 will be dominant. So that's why thinking word will be more dominant here. And at the end, what is we are getting is z1. And as I showed you previously from the starting, that what we need is at the output is z1, z2, z3, and that z1 is now here. Where we, yeah, here. So sum. So what we are doing is we are just having v1 and the z1 is this thing, correct? And similarly z2 we can get, and we'll call it as sum, right? So now let me just go to the paper, and this is the summary of the thing that I just discussed. That is what we are doing. We are multiplying query with this kt, then then dividing it by the dimension of the key vector, then taking the softmax and then multiplying with v, right? At the end we are multiplying with v, and whatever we get is our z. So let me just go to the paper that here. So until now, what we are discussing is this thing. I'll come back to the architecture later, but what we did is this thing. So whatever that we get after this multiplication is nothing but, sorry. So whatever we did, so this is the thing that we are doing, and this is called attention. So this is called attention function. So sometimes you might, like, someone ask you in the interview that explain attention function. So you can explain this entire thing from this paper, and like if you'll explain it, this thing thoroughly, you will get everything, each and everything, and no one will ask you further question, right? Because this paper follows BERT, GPT to everything. So this is the base, and if you will explain this, you are good to go. You will crack the interview, right? So whatever I explained, everything is written here. So after this video, as I said, this paper will be very easy for you to read. Now, so, and thanks to Jay Almar, because I also followed the same. So now this Z we get. Now what about multi-headed attention? So again, let me just go to the paper that here what we had was the attention. So now what is this multi-headed? Right? Until now what we covered is we are giving the input embedding, that is we are converting into 512 dimension. So until now we just know these two blocks, input embedding and inputs. That's it. And we know now attention, but we don't know multi-headed. So let's move to multi-headed, then we'll see what is positional encoding and the rest of the things. So here now he wrote the beast with many heads. So that's why it is called multi-headed attention. So previously what we did was, for thinking as well as machine, we were having the same vectors, like same matrix WQ, WK and WV, that is query, keys and values. But now what we are doing is we are using, for all the words, we are using different matrices, that is W0Q, W0K, W0V, and similarly W1Q, W1K and W0V. And after that, of course, we'll get different many outputs. So if we have like 7 words, then we'll get sorry 0 to 8 words, so z0 to z7, so we'll get z0 to z7. So what we'll do at the end, we'll concatenate all those, and one more thing is there, we'll multiply again with some weight matrix, that is again there is one neural network with some parameters, weight parameters, and whatever we'll get is the final z here. So this is the also attention function, but it is multi-headed attention function. This is the output of the multi-headed attention block in our research paper. I hope I am able to connect the dots here. Now, what we get is, this is the entire thing. This is summarized by him. That is whatever we are doing entirely. This multi-headed thing he summarized here. And at the end, you can see that this is giving more, it is referring to the animal, right? So until now, in this, what we finished is input, input embeddings, multi-headed attention, correct? Now let's focus on positional embedding. So it's also very easy that representing the order of the sequence using positional encoding. So what does it suggest is that, let me just try to cook some example. It means that if I'll say that this is ye shuish yudiante, so it means like, here we don't know that ye shuish is the second word, yudiante is the third word, because at the end we are giving input as 512 dimension. But it will be better if we can have, we can say that ye is the first word, this is the second word, this is the third word, something like that. That is, if we'll know position, because in translation, especially language translation, if we have like, because in some languages word a verb is in second position, but in some it is not, it might go at the end or somewhere. So it will be good to know the position of the words as well, and this is nothing but the positional encoding. So you will, if you will just read this positional encoding thing, you will get it easily. So I just try to cook one example so that I can explain it in a very layman way. And so now we are done with almost all the blocks from the encoder part. Just the thing is left is additional and normalization. Addition and normalization, that we'll see what is, as we already know what is normalization, but we'll see addition and normalization. And the one important thing here is that you can see there are skip connections. These are skip connections. So this is the same as ResNet, that is residual net neural network that we used in our image data. Like in CNN, there was many variants, and there was one ResNet as well. So what we are doing in the ResNet is that, in this skip connection is that, if this word is like, this attention is not useful for me, even I'm getting some attention function output, but I think that that is very low and I don't need it, that attention, then we can skip this attention block. I don't need it, and I'll go to some other block, next block, because we are having 6 number of encoders, right? Even we might have 12, 20, whatever. So even the same thing is applicable at the decoder part. And this is why they are writing this skip connection, that we can even skip and go directly there. The same as in residual net or ResNet that we call while we discuss our convolution neural network, correct? So what we are left is with addition and normalization, and then I'll continue this JLMR blog because the video is quite a bit longer now. So I hope you enjoyed up until now, and why is the need of the attention. And I'll also discuss the paper which is from the Jacob University in Bremen, I mean, and that will give more clear picture about the attention as well. But here as well, you got why we are using the attention thing, because we are getting some score. So I hope now the things is clear that why we are using query keys and values. So stay tuned and we'll continue from this point. Thank you.